Right, so we saw that there are some similarities in the structure of the balance laws, and in fact, so we can generalize it now here by introducing what we call here master balance law. So basically, write it for any quantity of alpha, right? So in this integral form, basically, what we are saying here is that whenever if we measure that quantity alpha and if it changes, right, and the change is again so with time, so the differential when dt of that alpha changes, so that is caused by two factors, right? So we have these sources for this change are, so there is a that the volumetric supply, so which we denote here by xi, right? Or and in addition, that can be or a combination of these two, that is surface flux, right? So there are two of these factors, and so one comes from the through the surface, hence the integration over of the surface area, or this volumetric supply, and hence the per volume, so that is the volume integration. And you can see there's lots of similarities with our with what we just have seen for the mass density and linear balance and for the angular momentum. And we just will see how to which alpha, xi, and phi this would correspond. And so this is again in integral form, but with a few standard tricks actually. Basically, one is that we're looking into the integration material time derivative of the integral, and then we obtain the second term that is related to divergence. So it's a standard operation, would apply the same way also for any argument here alpha. And then for the second term, here we typically use divergence theorem. Then we can unite all them together under the volume, so we can convert the surface integral into the volume integral, and then we can combine all of them, and then we demanded that must hold true regardless of our integration. So we do the localization of the law, and so hence in local form our balance equation will look like that, right? So again, from the time derivative, this additional term that comes from that integral term, divergence v, right? and here we have this local form of for quantity alpha, and once again, so phi here the surface flux, and xi is the volumetric supply that causes the change of that quantity alpha. So now let's just illustrate that more based on the example that we already had for our mass density, linear momentum, and angular momentum. So for that we have next we'll have this this table, right? And so once again, that 340 is that our mass balance law, mass principle. And now if we start from mass density, so we assume that we have a closed system, so there is no set line, so material doesn't grow in the volume, and there is no new particles or mass added through the surface. So we simply had the first term here, d rho dt plus rho d divergence v equal to 0. So we didn't have the second terms of that, but we had that. And when we wrote that, so the second term for incompressible materials actually dropped, so we didn't need that. Okay, so with linear momentum, so our linear momentum is the multiplication of v rho, right? And so for that, we had, so the volumetric supply was the body forces, right? But for the, so this is a linear momentum, right? So to basically, to that would go exactly in here, right? That alpha and in here. And now the volumetric supply would be our body forces, right? So per volume, per unit volume, and then the surface flux would be represented by sigma, which you remember was connected to traction that we applied on the surface, right? And so you can just see that in that form 340 is transformed exactly into that form of 326. Again, divergent sigma b. So these surface flux here, b is the volumetric supply, and we have that v rho that it represents that quantity alpha, right? That is caused to change, that linear momentum that is caused to change through the volumetric supply of surface flux. So this angular momentum, so we have a similar term, so but we multiply it as dot product r, so we have r cross product v rho, and then the volumetric supply. So basically everything looks exactly in similar manner. It just we multiplied everything here with r cross product. And of course, yes, we could now go ahead and basically substitute all these terms, right? Going instead of alpha here, and also instead of alpha here, and put that rho b here as the volumetric supply, and then the divergence phi will be substituted with divergence rho sigma, and so then we could write the equation that would appear here. But we know that all this with the help actually of the linear momentum balance, the angular momentum balance, which becomes by far more compact and more simple, and that the only term that survives is that the sigma multiplied by the Levi-Civita, and hence we could claim here that sigma transpose. Of course, in this form it it doesn't illustrate the balance law 340, but so that this is still does hold, it holds true indeed, and so it just we need to work rather hard to actually to simplify to sigma that. But the in general the angular momentum would of course be written in this way, by you can reconstruct it from 340 just by substituting what is the sources, volumetric and surface flux, and again the angular momentum coming in here. Now, so this is our the Eulerian description, right? So this is where we have some complications, and already mentioned that in solid mechanics the Lagrangian description is sometimes more preferable, right? So when we write everything in the known, in the undeformed configuration, in the reference state. So let's look into how these balance laws are transformed and read into the Lagrangian description. So again, the motivation to look into the Lagrangian description is that in that configuration, when we define our boundary conditions, we do know our geometry, right? You can think about that complicated potato, somebody that our soft material that you're going to apply forces on the boundary or as body forces. It's in order to properly define this traction and boundary condition in the deformed configuration, you actually need to know that deformed configuration, which typically you wouldn't know. So it's more convenient for you to have a way to define the boundary condition in the undeformed configuration, right? When the basically your starting point, when the geometry is known and you know where you start to apply your forces. However, then all the equations that we wrote at the balance law we wrote already for the current configuration, for the deformed configuration, and that will pose a little bit of difficulties of how we define the boundary conditions that our differential equations still need to satisfy. So therefore, here it's more convenient for us to describe this balance law and these equations in the Lagrangian description. Now, for that, we actually need to recall the important quantities from the kinematics in a transformation of the volume in area element. So here they are summarized. And you remember that the change of the volume element is defined, and so this is the volume small volume element dV in the current configuration, and dV0 is the volume element in the reference or undeformed configuration. And they are related, and we have shown that back then in the kinematics. They are related through this the determinant of F. So right, so we determined that J is that F, and the determinant of deformation gradient F is basically relates you the change in the volume around the point where that F is known, right? So in a similar manner, when we use that nonsense formula, right? So that is related as the nonsense formula, nonsense equation. So when we related the area element NDA in the deformed configuration, and n is normal to that small area element, to the n0 dA0 area element in the undeformed configuration. So we put 0 here to indicate more specifically that these are the measures in the undeformed configurations. And again, so that n0 is the normal to that small area element in the undeformed configuration. Orientation can change, also the area itself, the magnitude can change, and the transformation is twofold. So it also includes the determinant of F and the deformation gradient F itself. And once again, so just to remind you that we quantify that the change in the volume as the area as a vector. The area element is a vector. It is characterized by the area itself, but also the orientation of that area element. And so the so the transformation then is defined in the following way. So the quantity itself, and it also connects the terms that so we have this alpha, psi, and phi. For this our balance master balance law, and so they come as different integrations here, right? So that's so this integrations with volumetric integration for alpha, volumetric integration for psi, and area integration for phi, for the surface, for the surface flex. And hence you will see that the transformation between these quantities are also different. So these that are coming, these volumetric integrations, they transform by using J, right? So they appear in J here, right? While the one that comes from the integration, that the flex term, so transforms by the use by the transformation of the area, and hence it has these terms similar transformation as it was here in the Nansen formula for the transformation of the area, right? So this is the terms that comes from the flex, and again, so another important point to notice here. So we're going into the Lagrange description. So our independent variable here is the x as opposite to the one that we use in the Lagrangian description. So our x is our undefined configuration position vector, right? And hence we have this the different notation for the time derivative that is correspond when we hold x as fixed when we take the derivative. Now as a result of that, our life is actually will be easier here, as we're not we don't need to deal with this material time derivative of a spatial function. So all right, so let's then continue and apply that. So first into the local form, and then write how these mass, linear, and angular momentum balance laws will be written in the Lagrangian description. All right, so the local form, our balance law in the Lagrangian description will look similar to what we had before. The one thing to notice here is, again, so we have much more simple differentiation with time, the time derivative, and so since we're in Lagrange description, so note that we have that capital D here, meaning that we take the derivative, the divergence operator, with respect to the 2x, to the position in the undeformed configuration. So just to remind you that means that if we have the capital D here, so then that we'll have x here. As opposite, if we had a small d here in divergence, that would be y, so then we would take the time derivative with respect to position y, but this is again Lagrange description, so Lagrangian description, and so we have x. Now, so let's fill the same similar table of these things, right? So this is a general form for the balance law in the Lagrangian description, and now we want to write it for the mass, linear momentum, and angular momentum, the measurements in the in these configurations. And so for mass, everything will become very straightforward, right? So we have rho 0 for that, and again, so that is related to rho through multiplication with j. So that will directly we can obtain the relationship between the mass density in the reference and current configuration. So just by multiplying it with j, so that's a factor for us. Again, so this is a volumetric measure, and so then the balance law for mass will be extremely simple. Again, we assume that it's a closed system, so there are no sources, and so we'll have just d rho 0 dt. That will be our conservation of mass law. And so for the linear momentum, so we have the term for the linear momentum, again here rho 0, so substitute it right here, so only one term. Then we have the body forces that are recalculated into the deformed configurations, and that B0, also by the use of the factor of J, right? So that relates the volume. And then now for the surface term, we have stresses, and we have a different measure of stresses that we need to actually still to figure out what is the measure of stresses in that undeformed, in that reference configuration. And so the angular momentum is also similar in that way. So we have so our quantities that, okay, the angular momentum was substituted here instead of alpha 0, and so this is the term that comes from the body forces, which we, in a straightforward manner, we can recalculate and relate it to B, to the body forces in the deformed configuration. So again, by multiplication of with J, so basically we need to multiply B by J, by the determinant of F, and that will be B0, the same way as for the density. And so we again have this similar factor of stresses, but this must be a different stress measure. So we will need to look into that. So in fact, that's where we need to come and actually define this this stress measure, which is in the literature called the first Piola-Kirchhoff Stress Tensor. So we're going to look into that. All right, so so this is the our introduction of that new measure of stress as the first Piola stress tensor. So to start from something very trivial, so so we have this the small force element that is resultant force attacks on that small area element, so dA, and so through that we introduce the traction vector that is just multiplication of that by the area, and the traction vector is defined as a force divided by that area element. And so this is how we would do that in the deformed state. So the area element in the deformed configuration, the current configuration, the actual one that we are looking at. But it also can be, of course, done in the undeformed configuration. So the same, so by mapping that area element into the reference configuration dA0, and identifying with that the corresponding traction in that undeformed configuration. So, but of course, they need to produce the same resultant force that is acting on that small element. So now with that, we can so we could use the Cauchy theorem and connecting the traction and the stress, right? So this is our Cauchy theorem. Tell us traction is defined through a sigma and the normal orientation n, and so in similar manner, so we also almost finally define our new stress measure in the undeformed configurations, this first Piola-Kirchhoff Stress Tensor. And now with that we can, what we're just doing, we're going to basically substitute those terms back in our initial formula here instead of the traction, and instead of the traction in the undeformed configuration. And so then we end up with the formula that we have sigma nda equal to that p n0 dA0. And then here we that's exactly the moment when we should realize that there is a connection between nda and n0 dA0. This is a familiar term, which was in fact, so this is basically the area element, that vector element nda, that was transformed into n0 dA0 or vice versa through by the means of the nonsense formula that we derived again back in the kinematics section. And so this is exactly our nonsense formula. So with that we just could substitute either on the right hand side or on the left hand side. It will be more convenient. So instead of nda here, we can just write gf minus transpose n0 dA0. And then what we obtain here is that both of these parts, left part sigma, is multiplied by so we have so we can just write here that we have J sigma multiplied by F transpose and F minus transpose, and then we have that and 0 dA 0, and and that is still equal to what we have here, P and 0 dA 0. And so we can just pull that what we have on the right hand side to the left hand side, and just notice that we have the same multiplier here and 0 dA 0, so we can just pull it outside, and therefore we obtain that we have just this term, right? So this is J F sigma F minus transpose to this term here, right? Which we still keep in here, and the other term that P that multiplied by the same and 0 dA 0, so we just put it exactly here, so with minus, and by naturally from this equation we so that needs to be 0, and again, so that needs to be true regardless of our choice of this referential of this area element. So we, to satisfy that that it is equal to 0, we need to say that in fact that P is equal to J sigma F transpose, and so in that way we establish this connection between the this Piola-Kirchhoff stress tensor P that measures the stresses in the undeformed configuration and relates it to sigma of the true stresses or Cauchy stresses in the deformed configuration. And hence the name is true stresses, because that's the force that the actual stresses state of stress at the point feels in the actual current configuration. And P is nothing but a mapping of that stress into the undeformed configuration. And you can see that basically what happens is the mapping, if you again start thinking about the what happens here is that the force is still the same that is applied, but what you transform really is the area. And in a way, you can think of a very simple example when the orientation doesn't change, when you have the when you do the uniaxial tension, and so in small deformation that doesn't really matter for you, you just measure forces, and then you calculate the the area that initially was there, so the diameter of that sample that you pull, and so then your sigma was that force that you measured divided by the area. But in the large deformation, right, so you will see that the area actually has changed, and therefore you obtain your, so you will need to account for that, so the area will shrink because you pull it with the Poisson effect, and so and so your sigma will be changed through that factor. But if you divide it by the area in the initial configuration before it starts to change, because you just didn't want to measure the change in the area, for example, or it was not that possible, so then you in fact measuring the same force that you measure here by divided by the referential area, and so in that way that would be a measure of the component of K. It's very simplified by A0, so it was the initial area, right? And so there will be difference in the factor of the area here as you transform it. Okay, so this is just for one component, but just to show some physical meaning, some actual example that are quite useful, especially if you do this type of considerations. in simple experiment of a uniaxial tension. Right, so this unintentionally we have this formula put on the Piola, so these two phases that ended up in our important measure in our nonlinear elasticity or mechanics of soft material, this Piola-Kirchhoff, and the and so well, in some literature you would especially these taught by Italians would just call it probably the Piola stress tensor rather than Piola-Kirchhoff. Now, there one important note here, I think, especially related to the literature. So in some books, and actually one recommended for this course of by Ray Ogden, so that basically works not with the first Piola stress tensor, but with what is sometimes called nominal stress tensor, and actually also related to this example of the uniaxial tension. So where sometimes this measure of the stresses is also called nominal stress. And it should not be really confused with that. It's important that they are similar but not exactly. So there is this transpose side that makes them different. Of course, for the simple example here, when we use this uniaxial tension, and we have only this normal component here, so the transpose sign will not really matter. So they will have the same quantities, the same values, but in a more complicated deformation modes, and when you have the terms that are not on the diagonal terms of the components of the stress, so then you will start seeing, of course, different values in the nominal and Piola stress. Okay, so we introduce that. So we have this new guy Piola as basically as a source for this surface flat, right? So that before that, in the Eulerian formulation, we had everything written in the through sigma. So now we have P. So now we can entirely and fully formulate our balance law in the Lagrangian equation for the balance law. So let's go ahead and do that. So and again, it's helpful, but we already have told that basically the measures for the mass density and for the body forces in the undeformed configurations can be obtained by just mapping the actual body forces and the actual density in the deformed configuration by the factor J. Again, these are volumetric measures, and hence the mapping through J, so change in the volume. And then so the mass conservation law writes in very compact and simple manner. So this is our conservation of mass, again, so written in terms of the mass in the undeformed, in the reference configuration. And so the linear momentum is also written, is now written in a very similar way. So this is our d-rho 0 v dt, so this is the linear momentum. And of course, actually we can expand it very simply, but we can also use the mass conservation law, so that we can pull rho 0 outside, because d-rho 0 dt will be 0, because we need to satisfy the mass conservation. So then you have your familiar acceleration term dv dt multiplied by rho 0, that is equal to divergence p plus b0. And again, so this is p, this is our new measure of stresses in the undeformed configuration, and note that we have this capital D here, the divergence operator, just as a reminder for you, that meaning that we take the divergence operator with respect to our x initial position, the position in the reference configuration that we had. And so angular momentum is written a little bit differently here. So you remember that our angular momentum was such that we needed sigma to be symmetric. and now we also know that our P is is a different is a little bit different. So we have J sigma F minus transpose, and and therefore so P is not necessarily symmetric. Also sigma is symmetric, but then it's multiplied by F minus transpose, meaning that P is not symmetric. So basically we could say could now come and say, okay, if we multiply this with F from the right, F transpose, so then we'll have PF transpose equal to J sigma, but we also know that sigma is symmetric, so we can transpose the right hand side. So that would mean that, well, okay, so that equal to J sigma transpose. That would mean that PF transpose must be equal to the transposition of that, right? So that we can write that is will be FP transpose. So that must be FP transpose when we transpose that. So this is basically our angular momentum. So basically what balance. So we need what we need to ensure here that this term is symmetric. So PF transpose, if it's so that is a symmetric term. Why? Because sigma is symmetric. So because of that. So our angular momentum balance in terms of the first Piola-Kirchhoff stress tensor P is written in this form. So again, remember, P is not necessarily symmetric. In simple cases, it may be symmetric if there is nothing that happening on the diagonal, but in general, the first Piola-Kirchhoff stress tensor is not symmetric, and that is different from the true stress or the Cauchy stress. Now, all right, so one may wonder, so why we had the first Piola, and probably doesn't that mean that we have a second or third? So, well, yes, the answer is yes, partially. So we can introduce a second Piola-Kirchhoff stress tensor. Because one of the motivation is that we actually can make it symmetric by simply multiplying that with the inverse F from the from the left, right? And so then we can connect that second Piola-Kirchhoff stress tensor. And again, sometimes it's important to have symmetric measures so in our tensor for certain purposes. And so again, so we define the second Piola-Kirchhoff stress tensor by this multiplication of the first Piola-Kirchhoff stress tensor with inverse deformation gradient from the left. And so then we can substitute here that P definition through the formula connecting that to the true Cauchy stress tensor. So P is still equal to J sigma F minus transpose, and so we can substitute that here, and so J is the only scalar that we can move around without changing any order here. Oh, okay, so here is our formula for this connection. So we substitute it right in here, and so that's what we get. And so then it's easy to see that we can transpose this part. So we can transpose that this multiplication of the tensors, and this part will not change. So if we try to transpose all this, so there will be so depending on what part we want to work with, so we still will be obtaining the can be nice exercise. So we will still obtain the same result of F minus transpose sigma F minus transpose, because and what helps us here is that we know that sigma is symmetric. Right, so that's a good exercise that you can do, and so therefore this transposition operation basically returns you the same result after if done properly. And so then what is important to say here is that the second Piola-Kirchhoff stress tensor is symmetric. So one of the motivation for us to define the new measure of this stress tensor. Now, finally, we are going to just complete that with defining our boundary conditions again. So we have this all the balance law. So these are differential equations. So we can find a solution for that, but we also to fully solve the problem, we'll need to satisfy the boundary conditions, and which again can be defined through the traction, recalculating that in the undeformed configuration. And so then we can define the tractions that we define in the undeformed configuration here, and so then that will relate us to the stresses through the normal in the undeformed configuration, that we can relate it to the divergence P and the solution that we're obtaining there. All right, so the one important note here finally is that so this depending of what we define as a unit vector. So if we say that n0 in this configuration is a unit vector, this normal, then the transformation the transformation to n would be just by F minus transpose here. But if we want to also but that would make that n this normal vector in the deformed configuration, that will make it a vector that in general is not a unit vector. So the length of that can change, because F can also change the length of the vector when it acts on n0. And then we kind of redefine that n by dividing this new vector by this length, right? So this is because this is exactly the so this term is the magnitude, the length of that. So we divide it, divide that, and then n becomes a unit vector. So if we just don't do that, so we still can have a normal vector in the deformed configuration, can be directly obtained by mapping the normal vector in the undeformed configuration n0 with F minus transpose. However, n may not be unit vector, and this is the way just to normalize it, to divide it by the length, so making this a unit vector again. And in similar way, we do the transformation and can recover the traction in the deformed configuration and connects it to the traction in the undeformed configurations at T0. So with the defining the boundary conditions for here in the Lagrange configuration, we basically complete our consideration of the balance laws of our short journey here, and then now we are fully prepared to go and actually identify and start to define the material properties and start the constitutive law, which will be the next topic of our lectures. See you then.